Hello and welcome to this video. Now, in the last class, we ended up with, in the last video, I should say, we ended up with an expression that was something of this form, and this is the output of our system. We've supplied a unit ramp to the system, and this is the output we got from the system. Now, I asked the question, can we get a time function out of this? To get a time function out of this, then it means we want to take what is called the inverse Laplace transform. So the time function of this will now be our inverse Laplace transform. So the symbol for that will be, well, inverse Laplace transform of our y of s. Okay, so that's the inverse Laplace transform. I don't know if I actually need to write this inverse Laplace transform. I do apologize for my writing here. I don't feel I need to write it as I'm not taking time to write it neatly. Okay, so we now want to find the inverse Laplace transform of this. Now, we won't go ahead and find that out just as yet because I suggested that our solution will be an exponentially decaying sinusoid. Now, that is actually kind of wrong. Part of our solution will be the exponentially decaying sinusoid. Now, the reason why the solution is not an exponentially decaying sinusoid is that this is s raised to power 4, s raised to power 3, s raised to power 2. And if you remember, the particular example I referred to was s squared, s, and s to the power 0. So this will not just be an exponentially decaying sinusoid, but we'll get to that thought a little later. First of all, let me create a new function. Let's solve that new function, and then let's solve for the new function, and then we can come back to this question a little later. So let's say that instead, let's take out the s squared from the denominator. So let's have 2s plus 7. So 3 over s squared plus 2s plus 7. Let's assume this is our system, and let's now take the inverse Laplace transform of this. Okay. So to take the inverse Laplace transform of this, we're going to use the same two tables that we used earlier on for finding Laplace transforms. We'll use exactly those same two tables. So what do we know from those two tables? First of all, we know that the Laplace transform of sine omega t. So we're looking for something that looks like this. Because we have an s squared, let's just think sine omega t or cosine omega t. Now, for cosine omega t, if we find the Laplace transform of that, we have an s in the numerator. In this case, we do not have an s in the numerator, so maybe I shouldn't use cosine. Let me try using sine. Okay, so the Laplace transform of sine omega t is simply equal to omega over s squared plus omega squared. Now, this denominator does not look exactly like what we have over here, so we can't use this expression just as is. Let's try something else. Now, using the time shift theorem, you have the e to the power of minus at sine omega t. Okay, if you remember, this is a particular example that we did earlier on, or we did an example on this earlier on, and the Laplace transform of this was omega over s plus a squared plus omega squared, because what we have is f of s plus a. So wherever s was, we have an s plus a instead. Now let's look at this and let's actually expand this. What do we get? That gives me omega over s squared plus 2as plus a squared. That's this s plus a squared, and we have our omega squared still over there. Now this expression looks actually, if you want, exactly like this. Okay, it looks exactly like this. Or, well, it looks exactly like this, except that let me add one more thing. Okay, let me add one more thing, and then we can say it looks exactly like it. So let's bring one more of the theorems that we had. Okay, so in fact, let me remove that arrow I drew so that we now use the third one, because this one will, when I'm done with this, so I have ke, the Laplace transform of ke to the power of minus at sine of omega t. The Laplace transform of this, I'll just simply use what we have on the right here, will simply equal to k multiplied by omega over s squared plus 2as plus a squared plus omega squared. Now this looks exactly like what we have over here. And if that is the case, then we can actually solve, so when I say it looks exactly like it, let me try to illustrate what I mean. If you look at it, then we could say that our 2a is equal to 2, our a squared plus omega squared is equal to 7, and our k omega is equal to 3. And really, if I can find a, and I can find my omega, and I can find k, then I simply know that this is my time function. So let's go ahead and do that. Let's go ahead and do that. First of all, 2a is equal to 2. From this, it is obvious that my a is equal to 1. Okay? If a is equal to 1, then this second equation here implies that omega squared is equal to 6. Okay, I hope that's obvious. A is equal to 1. Take that to the other side, that becomes 6. So omega squared is equal to 6. In other words, we have our omega being equal to the square root of 6. Strictly speaking, it is plus or minus of the square root of 6. Yeah, so strictly speaking, it is plus or minus the square root of 6. Now, k omega is equal to 3. That means our k will be equal to plus or minus 3 divided by the square root of 6. Okay, and here we have a solution. Here it is, we do have a solution already. Now, k is equal to plus 3 over root 6 when omega is equal to plus root 6, and k is equal to minus 3 over root 6 when omega is equal to minus root 6. So in this case, I'll just stick with the positives and just simply say k is equal to 3 when omega is equal to square root of 6. The reason is that, yeah, that's convenient. It's convenient to just do that. So I'll just simply say that we have found a solution, and my y of t, sorry, that is y1 now, because we're dealing with y1 of s. My y1 of t is equal to 3 over root 6. Now, in fact, let me not just use the positive alone. Let me write the full thing here and keep it there, because that really is what it is. Okay, so plus or minus 3 over root 2, e to the power of negative, what's my a is equal to 1, e to the power minus t, sine of my omega is plus or minus root 6, plus or minus the square root of 6 multiplied by t. Okay, and this is my time function. Ideally, I should also include my u of t over here, and well, let me just go ahead and write it there. Okay, u of t. Maybe I should put this in parentheses so that we know that all of this is for the sinusoid. Okay, so this is what we have over here. This is what we have over here as our y1 of t. It will be convenient to just use the positives for k and for omega, but then this is the solution of our system. And so in this case, we have found the output, the time function, the output time function given a particular, given the ramp input. Now, this is the procedure we typically go through when we're trying to find the inverse Laplace transform. You start by asking a question, what do you know? Okay, so it's always a good idea to ask the question, what do you know? So let's take another example. Let's assume that we had a certain function, let's say p, a p of s that is given by, if you want, 3 over, now this is a simple example. I should have probably taken a simple example first before we, let me use the negative sign here, okay? Before we did the previous example, but since that's where we left off in the previous class, it was best to start from there. So let's say we had this function 3 over s plus s minus 1 and wanted to find the solution to this. The question we want to ask is, what do we know and what does this look like? So what do we know, what does this look like? Those are questions that we want to ask ourselves. So this looks very much like a case where, like the Laplace transform of an exponential function. So Laplace transform of an exponential function, e to the power minus at, is simply equal to 1 over s plus a. Okay, so that is very similar to this. And then if you remember, if you know your magnitude scaling rule, if you have your k e to the power of minus at, so if your function is scaled, if the amplitude of the function is scaled by a certain value, then this simply gives us k over s plus a. And if this is the case, I mean, it's straightforward. This looks, oops, let's redraw that. This looks exactly like that. In which case, we could simply say that our k is equal to 3 and our a is equal to minus 1. And therefore, we can simply say that our function p of t, so let's write it in full, the inverse Laplace transform of p of s is equal to, which is p of t, is equal to our k, 3 e to the power of minus 1t. So let's just make sure everyone is on the same page. Minus 1 is our a multiplied by t. So that is 3 e to the power t. Okay, and that's our answer. That is our answer over there. So when you want to find the inverse Laplace transform, you want to ask the question, what do you know? What does this look like? Let's pick one more example. Let's say that before, as I want to pick one more example before we go back to try to solve that we have one question up there that we have left unsolved. Okay, let's say we want to find the inverse Laplace transform of, say, 2s squared plus 2s minus 1. Let me multiply all of this by f of s. Okay, so I want to find the Laplace transform of this whole thing here, inverse Laplace transform, that is, of this entire thing here. Now, effectively, this is the same thing as 2s squared f of s plus 2s f of s minus f of s. And I have to find the inverse Laplace transform of that. Can I squeeze that in here? Inverse Laplace transform of this entire thing. Okay, so this, remember, this is a summation of various things. So since this is a summation of various things, each one of them can be dealt with on its own. So you could think of this expression here. And this expression looks very similar to what you have when you're finding the Laplace transform of, say, d squared of f. I was trying to decide whether to use f or to use a different function. Say d squared of f of t dt squared. Okay, if you have to find the Laplace transform of this, is equal to s squared f of s minus s f of 0 minus f prime of 0. Okay, so looking at this expression, we can come up with a, now take note that your f of 0 is a constant. Your f prime of 0 is also a constant. So that this expression here is, if you want, I'm hoping I don't confuse you what I'm about to say, it's effectively this s squared f of s minus k1s minus k2. Okay, where k1 and k2 are two different constants. So just bear this in mind. Let's assume that, okay, so yeah, just bear this in mind so that your k1 and your k2 are not necessarily 0. But if you look at this particular expression here, for this first expression here, it makes sense that my k1 and my k2 are equal to 0. And all I'm left with is my s squared parameter. This other function here looks like the Laplace transform of a first differential, and this is just a Laplace transform. So it makes sense that this our system here, the solution to that our system here, the inverse Laplace transform, will simply be equal to 2 times the second differential of f of t dt plus 2 times the first differential of f of t dt minus f of t. Okay, so that is our expression. We have found the inverse Laplace transform of this expression, and this is what we have over here. Note we have not solved for f of t, but then this gives us the yeah, so this is our inverse Laplace transform of that function as we were given. So I feel like I want to take one more example. But just before I do that, let me mention that One of the reasons why we use the Laplace transform is that we can use it for solving differential equations. So going back to the very top, if you remember the original system that we had, that gave us this here, we had a differential equation, and the differential equation, we had an x of t in that differential equation. Later on, we supplied an input, which was a unit ramp. We supplied that to that particular system, that the x of t, we now made it t u of t. And now we have found a way to almost resolve this. We've not completely resolved this yet. We resolved our y1. So far, we have resolved y1. Now, we have almost resolved it into a time function, and this is an exponentially decaying function, by the way. Okay, so what we have is a function that is effectively an exponentially decaying function. And by using Laplace transform, one of the benefits of the Laplace transform is that it helps us to solve differential equations. It can be used to solve differential equations just by using algebraic methods. Okay, so that's one of the benefits of the Laplace transform. Just thought I should mention that, not that we need that necessarily. So I'll take one final example, and that'll be it for this video. And then in the next video, we'll now look at solving the actual problem we started this video with. So let's just take one more example, and in here I just want a system where there is a summation. So let's say we had 2 over s plus 3, and I had say 3 over s squared. So if I were to find the inverse Laplace transform of this, I would just go ahead and write the solution to this, and I think by now you should have enough experience to know that this first expression here, the solution to that will be 2 exponential minus 3t, 2 being a constant, and then 1 over s plus 3 is the Laplace transform of e to the power minus 3t. This expression here divided by s squared looks like a ramp. Okay, it looks like a ramp, but you have a constant 3 there. So it is not a unit ramp, it's now 3 t u of t. And that's our expression. Note that this, so maybe I should actually go ahead and write this. This looks very much like Laplace transform of k e to the power minus at, which is equal to k over s plus a. This other expression, on the other hand, is very similar to the Laplace transform of another constant. So maybe let me call this k2, just so that we don't mix it up with this k we had in this previous one. K2 multiplied by t u of t. So if we found that, we end up with k over s squared. Okay, k over s squared. So this is very similar to that, k2, sorry, over s squared. And this is very similar to that, in which case k is simply equal to 2, a is simply equal to 3, k2 is equal to 3, and we come up with our solution over here. So that's it for finding the inverse Laplace transform at the basic level, and we'll push this one much further in the next video.